go for it. Okay. Including recording, we will have a go at doing the lecture. The topic for today is to introduce turbo machinery. Last week I was introducing the whole subject course. This time I'm focusing on turbo machinery. The reason turbo machinery is in here is because that's really been my life's work. That's what I do. And so I love it, and I want you guys to see just how wonderful it can be. And also that the coursework is only a turbo machinery exercise. So I've focused on it quite strongly, so it's also in your interest to understand turbo machinery to get a decent mark. I have some simple problems to be as examples, which will take probably half an hour or so to go through. I'm going to do those immediately after the lecture. I think that's the best time for them. It does mean that you'll be going from receiving the lecture material to immediately seeing examples on it, which means you don't have time to read and reflect. But I think it's probably the best structure that we can put together at this time. Okay, so this is the contents list that we have for the introduction to turbo machinery. Shan't read it out because you'll be able to read it on the screen. In every lecture that I give, I include a list of things which I believe you should learn. The intention is that when you're revising, this is a quick way of checking, have you got it? Have you learned what's supposed to be in this lecture? I won't read it through now. There are, about 7 or 8 bullet points there. And I think when you've done your revision, you should look down through that list and say yes, 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 yes. And if you don't say yes, then read the lecture again, because that's the information I expect you to pick up. And if you do, you should be strong in the examination. Okay, turbo machinery has been around for at least 2,000 years, and probably before that, but there's no records, so we don't really know that it's happening, and probably archaeologists don't recognize a turbine if it hits them. Here we have a list of dates ranging from 50 AD, about 2,000 years ago, up to the Second World War. We have a list of artifacts which are clearly turbo machines and have been recorded as such. The first is really a parlour game, a toy, rather than a useful machine, but nevertheless it's a so-called hero's turbine, which comes from Greece. No, actually Alexandria isn't Greece, is it? It's Egypt, to be correct. It comes from Egypt. And it's there's a picture of it later on in the lecture. It's a spherical body heated by burning coals with expanding steam inside it that spins round. And that spinning round is the turbine function. From Persia in the year 500 AD, obviously modern day Iran, there's a vertical axis wind turbine that has been found called, I don't know how to pronounce it, but Panemone is how it looks to me. And so this is the first example of a recognizable, useful machine driven by the wind. We have, from Portugal, a wooden water pump impeller dating back to the year 500 has been found. We have in 1629 Giovanni Branca in Italy, who was talking about impulse steam turbines. I don't know if he made one, which would have been more remarkable, but he certainly described them. In 1705, Papin in France recognizably described a centrifugal water pump and recorded it. In 1750, a guy called Euler, who was a famous mathematician, I believe Swiss, applied Newton's laws of motion to the turbo machinery and showed us how to calculate the power of a turbine or the amount of work that a pump would require to drive it. This is known as the Euler work equation, and I will be teaching you how that is derived and how to use it during the course. So Euler is definitely on the map and is 250 years ago. So it's a well-established technology. We have Baudin in France, who named turbines using Latin, apparently. Francis in America in 1851, who developed the Francis turbine. The Francis turbine is a rather special machine, one of very few, which is both a pump and a turbine. So you can use it for pumping water up a hill, and then you can use the same machine to take energy out of the water coming back down the hill. So if you have a pump storage scheme where you're putting water up into a lake during the night when nobody wants any electricity, and then in the morning when they all switch their kettles on, you let the water back out of the lake through the Francis turbine and the power comes out. So that's they're amongst the biggest and most powerful and most efficient machines in the world, are the Francis turbines, so very impressive. Reynolds, Osborne Reynolds, who was at Manchester University, patented the multi-stage centrifugal pump, and he's also the guy who we remember every time we talk about Reynolds number. For me, this is particularly significant because I did an apprenticeship at a company in Manchester called Mather and Platt Limited that no longer exists, and Osborne Reynolds worked with Mather and Platt and had the manufacturer of the first ever multi-stage centrifugal pump. So I was walking directly in the footsteps of Osborne Reynolds when I was at Mather and Platt. Charles Parsons invented the multi-stage reaction steam turbine. Very significant. Almost all the electricity we use is still generated by that process. Later on in the lecture, I'll show you a boat which he designed called Turbinia, which was historically very important. Rayleigh, who I think was a British physicist, I don't know much detail about him, he came up with a concept of dimensional analysis, which is the absolute cornerstone of fluid mechanics and turbomachinery. And this lecture will describe to you the basic process of doing dimensional analysis. Reynolds number is one of the results of dimensional analysis, and there are many other such numbers. They're all, as the name suggests, dimensionless, and that is the key to their value. Parsons pops back in again because he then patents a multi-stage axial compressor, the world's first. But as is typical in Britain, he patented it but never got it working. 15 years later, the Germans had it in the O'Hane engine, which flew the first ever jet fighter. So the axial compressor was made by Germany and invented in Britain, as was really the gas turbine. It was invented in Britain and made in Germany. The Germans have much more ability to complete their processes. Britain seems to just dream about possible ideas. Whittle patents the jet engine when he was an undergraduate in Cambridge, which I always think is a fabulous student project. You know, he dreamt up the gas turbine and he patented it. And then 9 years later, Germany is flying a gas turbine. It took Britain another 4 years. So Germany takes the invention and makes something of it. Britain makes the invention. Oh, do ask questions. Have you got one in mind?
Not exact question, but in relay, is it dimensionless? I heard you say dimensionless.
Yeah, the process is dimensional analysis. So we are analysing things from the viewpoint of what dimensions are present in the numbers. The end result are dimensionless groups. And these are numbers which, as the name suggests, they have no units. And their power is that they have no units. It makes them applicable across a huge range, and that's something to be understood. But everyone, including Monty, do ask questions as soon as they come to mind. It will help us all make progress. This is an attempt to show you the sheer range of activities I'm talking about. It is an enormous number of different products with an enormous number of different behaviours, all of which can be described collectively as turbo machines, or as I've written here, rotor dynamic machines. The implication being that the fundamental process involves a spinning something inside a fluid, whether it's pumping or extracting power. Rotor dynamic machines. We have a range of groups of different rotor dynamic machines, which I've done in the green bubbles. We have hydraulic turbines, wind turbines, gas turbines, fans, rocket pumps, steam turbines, wave turbines, turbochargers, water pumps, compressors, propellers, and air turbines. I won't read all the boxes around the outside. These are examples of the group that I'm referring to. But hopefully you can see that there's a vast range of different products in here, and they're all using the Euler work equation. They're all putting energy into a fluid or taking energy out of a fluid, and in principle at high efficiency. Some of them are less efficient, but in principle at high efficiency. Anyone have any questions about that? Because I guess there's quite a number of words that you don't know. Yeah.
How to define turbine?
Define turbine.
Turbine.
Yeah, a turbine is a machine which extracts energy from a moving fluid and delivers it to somewhere else, typically as mechanical work in a shaft. That's a turbine. Did that work for you? You still look puzzled.
Yeah. Take the energy flow from the fluid.
Yes.
So for the air, for the engine,
Yes.
for the airplane, it's from the air or from the fuel energy make it.
Now, the difference here is I'm talking about turbo machinery. An aero engine is two pieces of turbo machinery. It's a turbine at the rear and a compressor at the front. And the turbine's job is to drive the compressor. So if you stand back, ignore what's inside the engine, and say, what does an aero engine do? It converts the heat energy from the fuel into kinetic energy in the jet. Now, the engine is not a turbo machine. It has two turbo machines in it, but it is not a turbo machine. And that's why it doesn't fit in with what I'm saying to you, because it's a heat engine converting heat into kinetic energy, which is to say work. That's the difference. Happy?
Thank you.
Thank you. Right, very briefly, the economic significance of turbo machinery. This course isn't an economics course, so I won't dwell on it in detail, but you should be aware that it is enormous. As I say, it's very hard to overstate the economic significance of turbo machinery in the modern world. Almost all the machines you can think of actually rely on the use of turbo machines. All electrical power is generated by turbines. These may be steam, gas, hydraulic or wind turbines, but nevertheless they're all turbines delivering the work. All commercial air traffic is powered by gas turbine aero engines. Most ships are powered by steam turbines or gas turbines. Even diesel ships rely on turbochargers. And a diesel turbocharger for a ship is a huge machine in its own right. About 2 megawatts of power is the shaft power of the turbocharger, shoveling the air into the huge reciprocating diesel that's driving the ship. Pumps are rather less exotic devices. They're used to deliver water to your homes and to take away the sewage that you produce. So whilst the pump, as I say, is rather more basic in its function, it's utterly crucial to the way we run our lives. And I started in the pump industry, so I always defend it. Internal combustion engines, whilst their prime way of generating work does not involve turbomachinery. They all have coolant pumps to cool the engines. And now, in fact, it says here some internal combustion engines have turbochargers. I think we've now got to the majority of cars have turbochargers, so there are millions and millions of them around. Even space rockets. Now, you wouldn't have thought a space rocket would have a turbine in it, but it does. It's got a thing called a rocket pump, and the rocket pump's duty is to pump the liquid fuel into the combustion chamber, and I'll be showing you some more detail of that later on. So rocket pumps are a critical part of spaceships. And finally, maybe this one is a joke, it's just cooling computers. But they wouldn't get very far without the fans to cool them, and that's for sure.
Some of them have, like, a proper cooling system inside.
There are devices, electronic devices, for moving heat around the place, but I think in the end they mostly need fans to ultimately take the heat away.
So I've seen, like, graphic cards, like, they have a proper liquid.
Oh, liquid cooling system, right? Yeah.
Like a radiator.
Yeah. I think it does control electronic design, the heat loss, and it limits the number of transistors you can put on a chip because of the heat loss from the system. Some basic terms being defined. Inside, when we're talking about turbomachinery, you'll find I immediately use the terms axial, centrifugal, or mixed. And these are geometrical statements. The figure in the top left here is an axial flow machine. It happens to be a pump, the way I've drawn it. The flow is along the axis, and the aerofoils hang radially. One is a rotor, the other is a stator. Axial flow machines tend to have very high flow rates, which is why it makes a great deal of sense for an aero engine to be an axial machine. You'll see later on that that's what O'Hain got right and Whittle got wrong, is axial flow machines are very good for aero engines. But the amount of work you can do inside an axial machine is limited, and it's limited to relatively low levels of work. So axial, high flow, low work. The centrifugal is the opposite type, bottom right, which is also known as a radial machine, and I don't apologise for the fact that I use both terms. Centrifugal sometimes and radial some other times, but the two names are equivalent. The important thing about the radial is the flow enters axially, turns through a corner and leaves radially. The leaving radially means that the blade speed climbs as the fluid goes through the impeller. The Euler work equation will show you why that is important. So the centrifugal machine tends to do a great deal of work. The pressure rise is much larger than in an axial machine, but the flow rate is low, because typically the geometry involves relatively small areas, and so the flow rate is much lower. In the middle we have the mixed flow machine, which is quite a rare beast. There are a number around, but nothing like as common as the two extremes. But the mixed flow machine in the middle has the flow travelling on the surface of a cone. So it's a conical flow. The radius is increasing, but the fluid is also moving axially. They can be very efficient. In the pump industry, the mixed flow machines are the most efficient designs. They have a medium level of work and a medium level of flow, as you might expect. The basic definition of what is a pump or a compressor is that it does work on the fluid. And what that means is the stagnation enthalpy, formally, if you're into thermodynamics, the stagnation enthalpy of the fluid rises. That singularly is what a compressor is. Turbine does the exact reverse. It extracts work from the fluid and the stagnation enthalpy drops. And so if you want a definition of what determines whether it's a turbine or a compressor, look at the stagnation enthalpy, which is to say the total temperature. One of the things I want to do is to make sure you're all comfortable with the ideas of static temperature and total temperature, etc. Because what I learnt last year is the people in your position don't tend to know. And it's critical that you do know, because you cannot answer the questions until you've understood it.
Does stagnation enthalpy then include the dynamics of the fluid?
Yes, it does. Yeah. Yeah. See, in fact, the stagnation enthalpy has the total energy of the fluid, all the terms added together, whether it's due to its motion, its pressure, its temperature. They're all in there. And it's a very powerful concept. And the more I think about it, the more I marvel at it, because it's an astounding shorthand which people have come up with to express the energy content of a fluid. If you stick a thermocouple in the flow, what it measures is the stagnation enthalpy. Well, the stagnation temperature, which is linked to the enthalpy, of course. So it's a concept which we need to, as I say, all become familiar with. Some machines don't have casings. They're still turbo machines. Some examples I could think of were fans, such as a fan for circulating air around a room or something like that. Wind turbines, most of them don't have casings, of course. And in that list should probably be propellers. Propellers of aircraft and propellers of ships. They all don't have casings. They're still turbo machines, and the oil work equation will still tell you how much work they are doing on the flow. All the rest indeed do have casings, so the rotating part is buried inside a stationary part. It's the norm in a turbo machine. Here are some pictures. I showed these in the introductory thing, so you've seen them before. The top left is a picture of the Heroes turbine, which is this spinning sphere for a sort of parlour game, just to show people something funny to look at. I think it burnt coal, boiled water. The water is injected through the side arms, which also act as hinges, into the sphere. Then the sphere has two angled pipes, one at the top, one at the bottom, which forces a jet of steam tangentially this way at the top, that way at the bottom, and the whole thing spins around as a consequence. And so I don't believe it was used in any practical way, but it shows great promise of understanding how the mechanics of the fluid are going to influence the mechanics of a solid spinning thing. In the middle there is a photograph of a centrifugal water pump, important to me because that's the machine I did my PhD on, and if you have very good eyesight you might be able to see there are some number of little tappings going in at the middle which are connected to a system of holes inside that measure the pressure on the surface of the vanes. The aerofoils in that are called vanes because that's the language used in the pump industry. On the right we have Parsons' Turbinia, which is a nice little story. It is a picture of a boat. Plan view at the top, section view at the bottom. It's the world's first steam turbine driven boat. It goes back to a time when the British Navy was the biggest navy in the world by far. And they were all powered by steam engines, reciprocating steam engines. And it was state of the art, and they were incredibly confident and world dominant at the time. And Parsons came along and said, if you use steam turbines, it would work much better. You would have much faster, much lighter boats. And the Navy told him, go away. We don't want to know about you. Very British attitude to new innovation. So what Parsons did was to build Turbinia, which is the world's first steam turbine powered boat. It's only a boat, it's not very big. It still exists in a museum in Newcastle, so it's worth going to have a look at Turbinia. And what he did was he found out when there was going to be a massive meeting of the fleet. The British fleet was going to be meeting in the North Sea, and they were going to have 50 or 100 destroyers, you know, because the British Navy was just enormous at that time. And he showed up in his little boat. And what he did was he could travel 3 times as fast as the Navy could. And so what he did was he arrived and he made circles round all the boats and just embarrassed the Royal Navy by showing them that his technology was infinitely superior to theirs. And within the year, he had a commission to build the world's first steam turbine-powered fighter ship. And within 20 years, they were all steam turbine-powered. So it was a clever trick that Parsons pulled to show that the technology really was superior. Other end of the scale, this little thing here, which is 4 millimeters in diameter, is a very modern radial inflow turbine designed by MIT. And it was supposed to be the power source for a laptop. The truth is that it could never have been the power source for a laptop, because the exhaust temperature from the gas turbine when it was running was 700 degrees C. And you could have predicted that with undergraduate knowledge in 1 hour at the start of the project, but the Department of Defense spent $30 million finding out. It didn't work, it wouldn't even turn. It's made out of silicon, using silicon chip manufacturing techniques to get the detail of the aerofoils. And it was designed to run at 2 million RPM, but it didn't run at all because they got the heat transfer wrong. But details can be looked up if you're interested. And then we have at the bottom the two machines which started this process off, really. On the right we have Parsons' machine, which was following his patent. Britain didn't have the technology to make axial compressors. As I explained, Parsons invented and patented but never made a satisfactory machine, and Germany picked it up and made it. And on the left we have the O'Hain engine, dating from 1942 during the war, the so-called UMO 004 engine, which powered the first fighters that went into service as jet engine fighters. That's enough of that, I think. The rocket pump. I mentioned to you the existence of rocket pumps. It's another thing that comes from the Second World War. There was an absolute explosion in science and technology during that war, and the Germans invented essentially the space rocket. It was in fact a flying bomb, the V2 flying bomb, and it used liquid oxygen and liquid hydrogen forced into a combustion chamber where they burn, and then accelerating out of a nozzle beneath the rocket, generating enormous levels of thrust. The liquid oxidant and fuel was supplied to the combustion chamber at about 500 atmospheres pressure, and that pressure was generated using a pump, and this is the pump. The pumps themselves are there. You can see the periphery of the impeller with the vanes, with a bit of luck. That's the so-called Stichstoff, which I think is the oxidant. And here is the periphery of the fuel pump, the T-Stoff pump. They're both classical centrifugal water pumps. There's nothing strange about them at all. You know, when I look at them, I just think it's a pump, nothing special. They're going very fast, spinning round at tens of thousands of RPM, which centrifugal pumps don't do, generally speaking. So they're high speed. And the thing that's driving them, which I find very amusing, is a turbine, yes, but not just a turbine, it's a steam turbine. It's the sort of thing that Charles Parsons invented. But if you burn hydrogen and oxygen, what you get is high pressure steam. So in a space rocket, what you've got available is steam. So you use steam to drive the turbine. The thermal design of this is a disaster, because this is a steam turbine at what, 700-800 degrees C? These are cryogenic pumps at about minus 200 degrees C. So the temperature gradients in this machine are fantastic, about 1,000 degrees between the middle and the sides. And you can bet that the design is utterly compromised by that temperature gradient. There's been very little progress in rocket pumps over the years because there are very few generations of rockets. You know, the Americans still use the same engines they developed in the Apollo system and the same rocket pumps. So it's one of the slowest developing products. Most machinery is innovated every 2 or 3 years. You know, if you look at a Rolls-Royce engine, every one is different from the previous ones because there's a continuous innovation going on, because there's a huge market, lots of different planes, lots of different customers, and a vast amount of money. Rocket pumps, very slow. So close behind this is this, which is a European development from 1999, so 16, 17 years ago, called the fast track rocket pump. And one thing they have got right now is the thermal design. And you'll see the turbine is no longer in the middle, it's at the end. So the turbine is now on the far left here. You can see the volute which is feeding in the steam, and the turbine blade is just there. And the exhaust is in that direction off to the left. But you can still see inside the machine are the two impellers now in side view. This is the impeller for the LOX, the liquid oxygen, and this is the impeller for the fuel, which is called RP1. I'm afraid I don't exactly know what RP1 is. I don't think it's hydrogen, it's some other hydrocarbon, but that's the ultimate source of the energy. So we have two cryogenic pumps back to back. The temperature of the metal here is going to be minus 150, minus 200, that sort of range. And the hot bit is now pushed out to the side and not integrated into the cold bit. So the design has improved, I think. But I like the fact that it's a space-age steam turbine, because I'm sure Charles Parsons would have found that amusing as well. Some idea of the range of size of turbo machinery, so that you have a handle on just what the machines might be like. Probably the smallest commercial turbo machine is the dentist drill. I don't know whether you've suffered the joys of having a dental drill inside your mouth, but it makes the most awful noise which resonates inside your skull. And it's spinning round at 450,000 RPM typically. It's driven by compressed air, and the air is accelerated through a nozzle supersonically, forms a jet, and the jet hits this little blue thing, which is actually, technically speaking, a turbo machine which is not that common, which is called a Pelton wheel. I won't be talking about Pelton wheels in detail, but the job of the Pelton wheel is to catch the jet and to turn it around and make it go back the way that it was going before, and that applies a force to each little vein. So if you look, there's 1, 2, 3, 4 visible veins, and if you look at the surface of the top vein, it's got a ridge in the middle. The jet plays onto the ridge, and then it's turned around and goes back the way it came. A Pelton wheel can be very efficient if it's done right, and they're used if you have a hydraulic power scheme where the pressure is very high. So if there's a lake at, say, 3,000 meters up a hill, and you can take the flow from that down a pipe and extract the power, 3,000 meters is too high for almost all other turbo machines, but the Pelton wheel will do it and give you about 92% efficiency. So they're very efficient machines. So the dental drill to the massive hydraulic machine, fundamentally the same machines. In terms of rotational speed, the slowest I can think of is 6 RPM. This is a wind turbine, a big wind turbine. You can always tell how big a wind turbine is by how fast it's rotating. The big ones go slowly, the small ones go fast, because the tip speeds are almost identical across the complete range. So the 6 RPM tells you it's a big one because it's low. 6 RPM is 1 revolution every 10 seconds. There are 3 blades, so it means a blade passing occurs every 3 seconds. So it's thump, 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 coming by very slowly. Now, looking at the range of mass flow rates, dental drill is about 1 gram per second, so 0.001 kilograms per second. Francis turbines get up to 700 tons of water per second. The big ones do. So I reckon in terms of mass flow, the Francis turbine is the biggest in the world. The volume flow rate, I've actually noticed this morning reading my foils that I have an error. The volume flow rate of the dental drill, I've said, is 0.001 cubic meters per second. where I said the mass flow is 1 gram per second. This is wrong. The volume flow rate is 1,000th of that. So I've got my maths wrong. This is not 10 to the minus 3, but 10 to the minus 6 would be correct for that. However, the biggest volume flow rate of any turbo machine is the big wind turbine. It's just enormous. We've got 100,000 cubic meters per second of air going through the wind turbine. The amount of work a wind turbine extracts per kilogram is almost nothing. It's scarcely doing anything at all. You know, literally 1,000th of what I was used to in the turbines at Rolls-Royce. So a wind turbine, you sort of look at it and think, it's doing nothing. But what it is doing is shifting a vast amount of air through it. And that is why its power is finite, because it's just got this enormous 100,000 cubic meters of air going through it per second. Tiny amount of work per unit of mass. The end result is a finite amount of power, which is what we're all used to.
What's the typical output of wind turbine? Is like 8, 9 megawatts?
They would be the biggest in the world. So typical is still about 2 megawatts.
2 megawatts?
Yes, yeah, quite small really. Yeah. Compared to a power station which can be 1.2 gigawatts.
Oh.
You know, that's a modern steam power plant.
Oh yeah, that's the next thing.
Yeah.
Sorry.
Well, no, I didn't address the wind turbine, so the question is fine. But the biggest machines in the world are steam turbines with 1.2 gigawatts, and there's quite a lot of those in the world now. And the smallest that I can think of, a bit unfair really, is the MIT micro turbine. The turbine did generate power. The gas turbine based on it didn't run at all, so the number would be 0. Pressure rises in pumps. If you look under your bonnet at the engine of your car, you've got about 1,000 pascals. That's 1% of atmospheric pressure rise in the water pump. It's enough to make sure that the water goes round. There's also a thermal siphon which helps it. The opposite end is a thing called a boiler feed pump, and this was one of the main products of Mather and Platt when I worked for them, so it's particularly interesting to me. About 300 atmospheres of pressure to force water into a boiler. So boiler feed pumps, they'll have about 7 or 8 stages. They're turning at about 3,000 RPM, and they're generating that pressure. Compressor pressure ratio for fans, if they're just ventilation fans, you get a pressure ratio of about 1. If they're the fans on the front of a Rolls-Royce turbofan engine, the pressure ratio is about 2. These are typical numbers for fans. But compressors can be put into multi-stage centrifugal, just as pumps can be made multi-stage centrifugal, so can compressors. And the limit is about 10,000 to 1 pressure rise. So an enormous increase of pressure. MAN in Zurich manufactures such compressors, and they're quite fun because the size of the impellers goes down and down and down and down, because the density of the fluid is going up and up and up and up. So the final stage is a little stage, and the first stage is a big one, and it's all because the pressure ratio is sky high.
Sorry, that number, 10,000, is it a limit because of the technology, or is it a limit because it's not theoretically possible anymore?
Oh no, I think it would be theoretically possible. At some stage in the process, depending on the temperature, the gas will become a liquid. I've never met one where you put a gas in the front and the liquid comes out the back. But certainly here the density is going up by orders of magnitude as it goes
So in
through.
theory, if you put enough pressure on any gas, it'll become a liquid?
Eventually, yes. But it also gets extremely hot because you have to do work on it to crush it. And that heat keeps it a gas. So it doesn't rapidly liquefy. But if your pressure is without limit, you'll get a liquid. Indeed a solid shortly afterwards. So, turbine pressure ratio, wind turbines just about 1, no discernible work at all. Multi-stage steam turbines have a pressure ratio of about 1,000 from boiler feed pump delivery to sub-atmospheric pressure in the condensers of the steam turbines. Now we get on to the technical topic of this meeting, which is dimensional analysis. In essence, what the scientists and engineers were trying to answer is how does a little one, this is a battery charging wind turbine of 1 metre diameter or so, compare to a big one. This is a wind turbine with a diameter of 60 metres, and it's quite an old one now with sort of 1 megawatt of power. And what happened was that Rayleigh found a formal scientific way of comparing these things, and that process has initiated a complete thought process in the turbomachinery business. This is how we understand machines. This is how we know how big it should be, what its efficiency would be, how much power it will generate, how fast it should go. All those questions are in the minds of the designer, and this process is how they answer the question. And as I've outlined here, the kind of questions that a designer might be asked is, what is the effective pressure ratio? Does it matter? How will the machine change if I change the pressure ratio? Or how does the absolute pressure coming into the machine change the efficiency of the machine? These questions can be answered, and the way you answer them is by understanding the dimensionless groups which control the behaviour. And that's what the lecture is about. I won't actually do the dimensional analysis of a wind turbine. I'll look at a classical incompressible machine and a classical compressible flow machine to show you how they compare. The conclusions of those sections, I mean, it's pretty dry sort of academic stuff, but the conclusions are very strong and very useful. So try and follow what I'm saying and see that the conclusion is really what you want, is how do I understand the behaviour of these machines? Okay, we've got to talk about methodology. The whole thing is based on one very fundamental and very clever observation, which you may already be aware of. If you're not aware of it, it's worth knowing because it will help you. And that is that if you write down any equation, no limits, any equation, and you write it down properly, so you have no mistakes in it, then every term in that equation must have the same dimensions. Are you aware of that? Some nods, some raised eyebrows. It is the case that every term in every equation must have the same dimensions. And this means when you're deriving an equation in an exam or any other situation, you should look at the equation you've written and ask yourself, do each of the terms have the same dimensions? If the answer's no, you've got it wrong. You need to change it. So you can check your own working by looking to see what the dimensions are in the individual terms. And that is the essence of dimensional analysis, is the recognition that an equation only stands, can only be right, if the dimensions of every term are the same. When I say every term, I mean every term added or subtracted. The terms which are multiplied together as a conjunction must have the same dimensions. But it's the terms which are added and subtracted have to be all dimensionally identical. Otherwise, the mathematics is wrong of the expression. Now, in order to carry out this analysis, we need to be able to work out what the dimensions are of the various numbers that we need to use in design and in experimentation. And I've chosen an example here. I've chosen it because it's one of the most difficult that people tend to get wrong. So I'm looking at the dimensions of viscosity. Now, viscosity was defined by Newton, shown here. The shear stress is the laminar viscosity times the velocity gradient du dy. In order to evaluate its dimensions, we need to understand what dimensions we'll be referring to in turbomachinery, and they're listed here on the right. We have M for mass, kilograms in SI, L for length, meters in SI, T for time, seconds in SI, And theta I won't be using in this lecture, but if you have to bring it in, we use theta for temperature, which is Kelvin in SI. So these are the 4 dimensions which come in to turbomachinery. And there are only 4. There's nothing more, just these 4 to understand. So the question I'm trying to answer in this little bit of working here is what of these dimensions are present inside the viscosity mu that Newton defined. The process here, I won't bother reading it out to you, you can check it through for yourselves, is very simple. We recognise that shear stresses are force per unit area, that Newton's law tells us that force can be expressed as mass times acceleration, and so on. And it's just basic algebra to get you down to the final statement, which is that the dimensions of viscosity are the mass divided by length and time. I invite you to check that through and confirm that it's right. If you find it's wrong, please tell me, because I will need to know. So the dimensions of viscosity are defined there. We'll use that in a couple of pages' time as part of a proof. There's a rather silly theorem called the Buckingham Pi theorem. I don't know anything about Mr. Buckingham, but it's Buckingham Pi theorem. What this does is to tell you globally what's possible with a dimensional analysis. He says that if the number of independent variables in the problem you're addressing is n, and the number of dimensions in these variables is r, so the maximum for r is 4 for turbomachinery, then the number of dimensionless parameters you need to describe the behaviour of the machine is n minus r. This is Buckingham Pi rule. I don't think it really makes any difference to know that, unless it comes up in an exam question. And then you might benefit from remembering Mr. Buckingham and his pi. But I don't take that awfully seriously, Buckingham Pi. It's a very simple idea. Here we go through the derivation of the dimensional analysis of incompressible machines. So broadly speaking, water pumps, water turbines, those sort of things. The number of independent variables, the variables you might choose to vary to make a new design for a machine, is 5. We have the volume flow rate, the diameter of the impeller, the rotational speed of the impeller, the density of the water, and the viscosity of the water. Those are the 5 variables. I don't really think there are any others. That ties it down. It gives you all you need to know about any given design. On the right here in a box, each of those variables is defined. There are then 3 more variables which are the dependent variables. These are the ones which depend on the design that you've made. If it's a good one, the efficiency will be high. The pressure rise will be strong, and the work absorbed will be as low as possible, thinking of a pump. The thing about the terms here is the first one, eta, is a dimensionless group on its own right. The efficiency is a dimensionless concept, so it stands without any further adjustment. If we want to do the analysis for the pressure rise and the work, we need to non-dimensionalize those, which later on in this presentation I'll at least show you the non-dimensional form of the pressure rise. What we do now is we write 3 equations, which in some ways are very simple. They relate the efficiency to the 5 independent variables through a function called f1. Could be called anything, it's just f1. The important thing to realise is at no stage in this activity do you need to know what the functions are. So f1 is not defined and will not be defined because we don't know. The only way you can evaluate f1 is to measure it. You do the test. But dimensional analysis allows you to use that data to compare a complete range of pumps. So it's a very powerful process, but it's rather different from the process you'll meet in almost all the other lectures that you attend, where we attempt to analytically define things. This is not analytical. This is just a recognition that there must be an equation. We don't know what it is, but it must exist. And it's called F1. And it relates the 5 independent variables to the dependent variable. And we have F2 for the pressure and F3 for the work. All unknown and will not be known. And the point at the bottom is important, that they must be found experimentally. You could try and do 3D unsteady CFD calculations of the whole thing to begin to predict F1, F2 and F3 nowadays. When this work was all developed, it was impossible to run CFD codes, so we just did experiments. Here's the process by which the dimensionless groups are found. It's a stepwise elimination process where we play with the terms in the equation to get rid of the dimensions. The idea being, as I said at the start of the lecture, that a dimensionally correct equation has the same dimensions in every term. If we get to a condition where only one term in the equation has a particular dimension, you know it's wrong. You know it cannot be there, because it's the only one with the singular dimension that's not present in any of the other terms. Once you get to that position, you can throw it away. And that is the logic which is used to reduce the number of dimensionless groups, by throwing out the ones which are left with the dimension in. Let me show you that happening. We start off with the expression for the efficiency, which is F1 of those 5 variables. The next line down in the analysis, we write down the dimensions of each term, because we know that. So we have that the volume flow rate is volume flow rate per unit time, so it's L cubed over T. The dimension is simply a linear dimension, so it's L. The rotational speed is revolutions per second, so its dimensions are 1 over time. The density is kilograms per cubic metre, which is mass per unit volume, so m over L cubed. The viscosity, as I showed you in the derivation earlier on, is m over Lt. That's the strange one which you'd probably benefit from remembering, that it's m over Lt for viscosity. So we take a look at this and we say, right, now we want to remove mass from this equation. We don't want to have the dimension of mass present in any of the terms. How can we remove mass? Well, one way of doing it, possibly, no, there are 2 ways of doing it, up this way or up that way, it doesn't matter. I've got density over viscosity, which if you take the ratio of those two groups, clearly the mass flow is going to cancel out if I divide the density by the viscosity. So I get mu over rho. Sorry, rho over mu. If we now write down the expression again with the rho over mu in it, so I've changed the variable from being density to being the ratio of density to viscosity, is what I've done. If you write down the dimensions of the new equation, you now find that only the viscosity on the right has in it the dimensions of mass now. And the logic follows that since it's the only term in the equation with a particular dimension in it, it must be wrong. It cannot be there. So we eliminate it. We simply cancel it out. So viscosity now gone, but left in a new term, which is the ratio of density to viscosity. We now look at that and say, right, we want to eradicate time from this equation. Having eradicated mass, we now eradicate time. And time appears in a lot of terms. It's in the first one, the third one, the fourth one, and the fifth one. And what we do is we take omega, which is the rotational speed, and we divide the first term by omega, taking the one out. We divide the fourth one by omega squared, he says, without seeing that it's done. I've got lost somewhere. We want to get rid of time. That, the omega is the 1 over time which appears there. L is d, that's right. What happens to t over L? This term is the t over L squared, isn't it? Sorry. This term has disappeared because we've cancelled out mu, so this term goes away. That term is the mu of the rho upon mu term, which now it has time in it, needs to be multiplied by omega to cancel the time out. So that term comes from there. Phew, found it again. So now we have an expression when we write down this one, having put the rotational speed into the first term and the fourth term, we have an expression which shows the dimensions of each of these terms now, and only one of them has time in it, which is now the rotational speed. Following the logic, since it's the only term with time in it, it has no place in the equation, it has to go. So we delete it. And we're now left with three groups, which are dimensionless, has dimensions of length, and dimensionless. D is now the only term in the equation which has the dimension of length in it, so it doesn't belong, it has to be thrown out, and we cross it out. And we end up with two, that the efficiency of the machine is a function f1 of q over omega d cubed and rho omega d squared over mu. These two terms have names. The first is known as the flow coefficient, being volume flow rate divided by something. And the second is indeed the Reynolds number that Osborne-Reynolds proposed. You may remember, hopefully some of you do, what Reynolds number should look like. And you might be thinking, that's wrong. Shouldn't look like that. It should be rho v d over mu. What we've got here is rho omega d squared over mu. Anyone got any ideas why? Why is that a Reynolds number? Say again.
A corrected Reynolds number, something like that. We add something to, multiply it by.
No, in fact, it's a perfectly genuine Reynolds number. Any idea why? Anyone else? Is it dimensionless? I've told you it's dimensionless.
It's because that's the kinematic. Normally use kinematic viscosity.
We have rho over mu, so you could replace rho over mu by nu, which is the kinematic viscosity, but that doesn't really change anything here. No, the simple thing is that in Reynolds number we're used to seeing a velocity. There's no velocity in this equation, but there is omega times d. Omega is the rotational speed, d is the diameter, so the velocity is hidden in there, and then times d again, it's d squared, which is you expect to see in Reynolds number. So this is a perfectly genuine Reynolds number, it's just a bit written in a slightly funny way. Buckingham pi comes in. I can show you that Buckingham pi has worked. We have 5 independent variables. We have 3 dimensions in those. The number of non-dimensional groups is 5 minus 3 is 2. That's all Buckingham pi tells us. There should be 2 and we've got 2. So we can celebrate. Yeah?
How do you know which terms to take? Oh, I think I'm being stupid.
You're probably not. Have a go.
No, I am being stupid. I was just saying because I was like, how do you know that we're dividing by mu, but then I realised that
Yeah.
dimensions.
It is a... Dimensional analysis is a tricky kind of area because it's so unlike everything else you've been doing. And the truth is that the answer is not singular. This is a answer which is useful, but it's not the only answer you could get, and it's not the only correct answer, and that's what the next foil is about.
So could we try to get any correct answer? For example, if we go back to the last slide, if we divide we divided rho over mu, didn't we?
Yes?
If we did, vice versa.
Yeah,
Like
mu over rho instead.
instead.
I think from a scientific standpoint, it's completely satisfactory to do it the other way.
But we will not get like Reynolds number at the end.
No, you get 1 over Reynolds number as an answer because you've inverted it. But that's what the foil is about. Did you have a question? Or you're just stretching?
No, man. Would we get a similar result if we eliminated T to begin with instead of M, say?
I don't know. I've not tried it. Worth trying. You may get a different result. And the point is that dimensional analysis is not singular. There are many answers to the question. All of them can be judged as right or wrong, but there are many correct answers which can be written. And that's what my next foil is about, is dimension analysis and singularity. When I was taught this in Cambridge, I was unhappy. I didn't like it because of the doubts that you've nicely expressed, that, you know, what if you do it the other way? What if you make a different choice? The point is, from a scientific standpoint, it doesn't matter at all. It will still work, provided you're following the rules. You'll get different dimensionless groups, but their function and the understanding they could bring is every bit as good as the conventional dimensionless groups. Where the problem comes in is with human society. Because if you have redefined Reynolds number as 1 over Reynolds number, for example, or the example I chose here is a Reynolds number which could be based on the volume flow rate instead of on omega and d. It still works, it's still dimensionless, and it would function in terms of understanding the experimental relationship between a big one and a small one of a particular sort of machine. The problem is that in human society we have a conventional way of working, and Reynolds number has a conventional form. And if you redefine it, no one will know what you mean. And that, in the end, is why there is one correct answer, because of what is accepted. It's not scientifically justified, but it's helpful because people will understand what you mean. And that really is the answer. This group would allow you to do everything functional you needed to do, but no one would understand what the hell you're talking about. Because what have you got volume flow rate in a Reynolds number for?
If at the end we reach an answer and we see, okay, it's 1 over something, can we just like make it the other way?
Yes, that would be completely valid because it's still non-dimensional. So inverting it doesn't change it, you know, from this understanding. There's a second problem which arises, and that is, you know, I've been talking about this as if the dimensions of a given machine can be summed up by one number. I mean, when you're designing a water pump, you have 1,000 numbers to define. How come there's just one number? And the thing is, from the dimensional point of view, the machine just has size. Is it a small one or a big one? And all its dimensions grow as it gets bigger, and all its dimensions shrink as it gets smaller. So there is only one degree of freedom. There is only one size number. But we arbitrarily choose to define that by the diameter of the impeller. You could arbitrarily decide to design it by the thickness of the impeller. There's nothing wrong with doing that, but you'll get a completely different number and confuse everyone else you're talking to because you're quoting Reynolds number based on thickness instead of diameter. Completely different number. So this is where you need, when you're given a dimensionless number, your first question should be, how is that defined? If you don't ask the question, you can't use the information. It's not unique information. It is not singular, and you need to ask the question of how it's defined. In industry, we have the problem of communicating coherently so that everyone understands what we're talking about and how to compare the different, you know, Rolls-Royce must have designed literally 1,000 different turbines. And somehow we've got to compare them. We've got to understand what's a good one, what's a bad one, what's a big one, what's a small one. These sort of questions all come in. And what goes on is we define a series of statements. For example, I'm a turbine engineer. That's been most of my work. For a turbine engineer, I know that Reynolds number is defined on conditions at exit from the blade row, where the velocity, viscosity, and density are assessed, and that the linear dimension that's used is the chord, the true chord, so-called, of the blading. If all those things are put in place, then I know how the Reynolds number changes, and so do all my colleagues, because they know to look at blade row exit for velocity, density, viscosity, and take true chord. Then the Reynolds number is singular, and we've tied it down. But you need all those additional questions, you know, where and what pressure and so forth. The compressor designers, they like Reynolds number too, and they know it's very important for their machines, and they base it at blade row inlet, where they take velocity, density, viscosity. They still use true chord, as do the turbine engineers. So it means that the compressor Reynolds number is on a completely different scale from the turbine Reynolds number. They're not the same. They're two different definitions. And one of the reasons why compressor designers and turbine designers don't get on with each other, because the numbers are different. So, no singularity, and you need to define where the numbers are taken. Now, if I quote to you a Reynolds number in an exam question, I will say where the velocity is taken at blade row exit or inlet, depending whether it's a compressor or a turbine. But you've got to be aware that no definition, can't use. There's nothing singular about a Reynolds number until you know how it's defined.
Just a reminder, the Reynolds number is always the same at any stage of the process, isn't it?
No, that wouldn't be true.
No?
No, the Reynolds number, if you look at it, has the dimensions of size, rho v d, so you have d, size in there. It has velocity in there, v squared, sorry, v. And of course density and viscosity as well. So a good example is if you take an LP turbine from an aero engine and you monitor its Reynolds number when the aircraft is taking off. Inside the engine, the pressure is then very high because you've got atmospheric pressure, which is factored up by the compressors by a pressure ratio of about 40 or so. And that air expands through two turbines, then gets to the LP. The pressure is still relatively high. That means the density is high, and the temperature is high as well, because you need high thrust when you're taking off. And when you get to cruise, the ambient air pressure goes down and down and down and down, maybe by a factor of 5, and all the pressures in the engine go down with it, because the engine is defined as a set of pressure ratios. All the ratios stay the same, but the absolute pressure falls, which means the density of the air in the turbine gets much lower. So the Reynolds number falls inside a turbine when you go from takeoff to cruise.
So, if it's not constant during the process,
Mhm.
then why is it so important, I believe?
Because that level, the level of the Reynolds number, actually tells you something about the way the fluid is going to behave. Because inside the Reynolds number, you know, if you ask the question, what does Reynolds number mean? You'll find in the textbooks, it says it's the ratio of inertial terms to viscous terms. So it tells you, broadly speaking, how much force the momentum of the fluid can generate compared to how much force the friction of the fluid can generate. And the size of that number tells you the relative size of those two, and it changes. The result is, with an LP turbine in an aero engine again, that the efficiency is much higher at takeoff because the Reynolds number is high, the boundary layers are thinner, the losses are lower, and the efficiency is higher. As the aircraft climbs and the pressure falls, the density drops off, the Reynolds number falls, you get thicker boundary layers with more loss and lower efficiency. It's very unfortunate. It drops by about 2 to 3%. And of course it's at cruise that you burn most of the fuel if you're travelling to America or around the world the other way. You end up burning much more fuel because the Reynolds number fell. So that for me, Reynolds number is incredibly important, but you've got to tie it down really carefully before you understand what it's telling you. Okay? Now, back in the pump industry, when we test a pump, this is one of the graphs that we produce. This is the flow coefficient you should recognize from the dimensionless analysis of incompressible machines that I've just shown you. That is the dimensionless head rise, known as the head coefficient. In the pump industry, we don't talk about pressure, we talk about head. Head is how high the water is, the head of water, and of course the head relates to the pressure through rho GH. So it's just terminology, but in the pump industry it's called head. So the head coefficient is dimensionless pressure rise. So the dimensions of pressure are the same as the dimensions of rho omega squared d squared. You can check that if you don't believe me. It's a dimensionless group. And as such, it can be related to the same pair of dimensionless groups we evaluated for the efficiency earlier on. And what this shows is an experimentally derived pair of curves which show how the pressure coefficient or the head coefficient compares to, or is controlled by the flow coefficient. And you'll see the curve has a broadly straight region at high flow coefficient where steeply the pressure drops off as the flow goes up. So you can imagine that the faster the flow goes through the pump, the lower the pressure rise. This is what we call a stable characteristic, and it's what we want. This is where the pump will not do anything funny and get into trouble. The curve peaks in this graph at about 40% flow or so. There's a maximum. At the maximum, you're okay, you're just stable. But the pump is getting dangerous, it's getting unstable, it can't really be sure what to do next. If you close the valve a bit further, so the flow rate drops down to, say, 25% flow here, you're now on a curve which has a positive gradient, which means that if the flow rate goes down, the pressure goes down, which makes the flow rate go down more. So the pump is unstable. It cannot pump stably on a positive characteristic. Now this is a feature of all compressors and pumps, that they become unstable at low flow rates. And it's a very important part of the technology of gas turbines. I'll talk to you more about that in a subsequent lecture. But just be aware that low flow is a problem. Turbines don't care. They'll work over the complete range because they're stable. Compressors and pumps fall over when the flow rate is too low. But the reason for this chart was to show you what is the effect of Reynolds number. We've defined Reynolds number as a variable that is important. It appears in the dimensional analysis and it should have an effect. And it does have an effect. The effect typically is as I've shown it here, which is that it just moves things a little bit, you know, maybe 1% or so. And the reason for this ultimately is because the Reynolds number in almost all the machines you'll ever meet is high. We have high levels of Reynolds number, which means that the flow rapidly becomes turbulent. It's unstable from day one, and the consequence is that all the designs are turbulent, so the change of performance between them is very small. And we end up with almost the same characteristic, ignoring Reynolds number. There are exceptions, of course. The MIT machine at 4 millimeters diameter has such a low Reynolds number that it's very unlikely to be turbulent. So it's a laminar flow, and laminar flows do a very wide range of interesting four-dimensional flow fields with separations and eddies and reattachments and so forth. The efficiency always drops off at such low Reynolds numbers, and the flow is entirely different. So for MIT to analyze their machine, they would need Reynolds number in there too. For most machines, we can ignore it. And it's very often the step taken in dimensional analysis to say, we assume Reynolds number is unimportant here, and move on. Okay, one of the jobs in the pump industry is sales engineering. And a lot of engineers are actually employed as sales engineers. Now, their job obviously is to sell things, but it's a technical job. It's not just a financial job, it's a technical job as well. And what happens is the guy is phoned up by a potential customer, or I suppose nowadays an inquiry form is sent through the web, which says customer A wants the following pump. Now, the customer in general, of course, is not an expert, doesn't know about pumps. All he knows is how much stuff he needs to pump, what pressure rise he'd like to see, and how fast his power source, whether it's an electric motor or a gas turbine, how fast it goes. And so he goes to the pump manufacturer and says, well, I want this flow rate, that head rise, and my machine is going around at this speed. What sort of pump are you going to sell me? And this is a very difficult question to answer. It's not straightforward. And the first question the sales engineer has to come up with is what type of pump? Should it be a radial? Should it be an axial? Should it be a mixed flow? And this is formally how he answers the question. The process is called specific speed. And you'll find it in all turbomachinery textbooks. They talk about specific speed. it's mathematically ugly. I mean, you've probably already seen that it's mathematically ugly, but it actually allows you to do something you can't do any other way. So it's kind of valuable. The underlying thought process is the head coefficient and the flow coefficient of the pump both have in it the dimension of size, length. If we construct a group which is based purely on those non-dimensional groups, which doesn't have size in it at all, we will have a special non-dimensional number which is irrespective of size. And that's what's going on here. The specific speed is called Sn. It's defined as being equal to the square root of the flow coefficient divided by the head coefficient to the power 3/4. The reason it's like that is to cancel out d. d drops out if you do it this way. There's the ratio of the two groups, and here's the ugly answer. Q to the half, omega, rho to the 3/4, delta p to the minus 3/4. But this was invented in the pump industry in the late 19th century. It's been around a long time, and it singularly tells you what type of pump you need to design. The values of the specific speed are shown in their effect on the diagram at the bottom of the page. The graph is a graph of volume flow rate, coefficient, Q over omega d cubed, plotted against head coefficient, and we have the characteristics of a number of different machines drawn on that diagram. From an axial machine, which is this long, low, flat curve, which has a specific speed of about 2 or higher, to, at the opposite end, a very high pressurized, very low flow radial machine, which has a specific speed of around 0.4 or lower. And in the middle we have mixed flow machines, which would have an SN of maybe 1 or 2, something like that. The point is that this number tells the sales engineer where he is in this curve, and he then knows what type of pump you want. Without that, he can't answer the question. What would then happen is he's got a stack of pages of information which tells him, as a function of specific speed, what pumps he can offer, and they're different sizes, different rotational speeds and so on. But the specific speed is tied down, so he knows he's addressing the right type of pump that the customer is after. I'll talk more about specific speed when we get through to the examples. Now, in a rather briefer way, because I find the elimination of variables rather dull, I'm going to address compressible flow dimensional analysis. So we now talk about steam turbines, gas turbines, centrifugal compressors, all those sort of things, things where the density changes appreciably and where the Mach number may be transonic. So we have high Mach numbers in them. The list of independent variables grows. We had 5 for the incompressible machine. We're now up to 1, 2, 3, 4, 5, 6, 7, 8. So there are 3 additional variables that come through. And that's still when we're ignoring heat transfer. So this is still an adiabatic analysis. If you include heat transfer, then you get 2 more terms, but we'll mention that later on. The 8 we have in there are the inlet pressure, called P1, the diameter of a machine, the mass flow rate through the machine, the temperature into the machine, the blade speed, U, the specific heat at constant pressure, the viscosity into the machine, and finally the ratio of specific heats. So they're the 8 parameters which are important. You go through the agony of removing each of the dimensions one at a time, and you end up with this expression, which is an expression for the pressure ratio. Note, pressure ratio is a dimensionless group, so it's a very active participant in dimensional analysis. It's a good group to have. Pressure's a problem because you've got to non-dimensionalize it. pressure ratio is a non-dimensional. The other non-dimensional we're interested in is viscosity, which is also a dimensionless group. So the pressure ratio is an unknown function f of 1, 2, 3, 4 groups, which have come out following Buckingham pi and excluding all the variables. We end up with these. As we've already discussed, they're not singular, but they are the ones that we conventionally choose, so you should be aware of them. The first is known as dimensionless mass flow. It appears in fluid mechanics in many different places. It's particularly important in turbines where it controls the mass flow through the engine as a whole. It is the mass flow rate times the square root of CPT1 divided by d squared P1. As we've said, it's a dimensionless group. It looks a bit ugly, but it's really important. It's one of the most powerful tools we have to understand what a machine is going to do and why. I'll give you more information on that as the time goes by. The next term is a dimensionless blade speed. It's U over root CPT. Now, CPT is, in fact, to be technical about it, the static enthalpy of the flow coming into the machine. But it's also closely related to gamma RT, which hopefully you will recognize when square rooted as the speed of sound. So root gamma RT is the speed of sound. Root CPT is closely related to the speed of sound. It's not the same, but it's related. So broadly speaking, this is the Mach number of the blades. We then have M over D mu. This is another disguised Reynolds number. M has density in it, and we have mu on the bottom, and if you write down the dimensions, you'll find this is Reynolds number. But it's how it turns out in a compressible universe, M over D mu. And finally, the ratio of specific heats is there as well. You may think it's not really needed, but in fact it is needed, because when you burn fuel inside an engine, the ratio of specific heats changes. For air, it's about 1.4, and for burnt kerosene, it's about 1.28. So it has a major effect on performance. So it needs to be there, otherwise you won't understand the behavior of the machines. So mu is in there. These words, I think, just describe what I've been saying to you, so we don't need to go through those. Right, so what do the characteristics of a turbine look like? Here are some sketches. The equation at the top, what we're doing is we're ignoring two groups. The two groups that we're ignoring are the Reynolds number and the ratio of specific heats. So we're taking the assumption that they're not very important at this stage. And we have therefore an expression which is pressure ratio against capacity and blade speed, non-dimensional. If you run a turbine and you plot the capacity and the efficiency against pressure ratio, you get these two sets of curves. The lower one is rather boring. It's the capacity of the turbine against pressure ratio, and it's mostly a constant height straight line. And this is because most turbines spend most of their lives choked. They are passing the maximum mass flow they can all the time. They never unchoke. So that means that you're transonic. The flow is getting up to sonic at the throat and then accelerating supersonically downstream. And the turbine is just flat and straight. If you look at a Rolls-Royce HP turbine, it never experiences anything other than the choked state. So even from ground idle through takeoff, up to cruise, through landing, all the time it's choked. And that means the flow angle is constant, the Mach number is constant, the thing is in a steady state condition. The only thing that varies is the level of the pressure. As the plane goes up, the pressure goes down. So the Reynolds number is moving, but the angles and Mach numbers are constant. So we're in this sort of territory most of the time. If, however, we run at particularly low pressure ratio, as the engine does when it's starting up from idle, things start to change. The capacity drops off and the curves depart one from the other because the rotational speed is changing. And if the rotor's going faster, the capacity is lower. If the rotor's going slower, the capacity is higher. So that's the tale of capacity in a turbine, relating the... Oh yes, I've played the trick. You may have noticed, those of you that are awake, that this has changed. At the top, it was n root CPT over d squared P1. Now it's n root T upon P. This is the form that's used in industry. That is the dimensionless form. And in industry, they cheat because it saves time and it's quicker. So this is a semi-dimensional group. Semi-dimensional. It's not a proper dimensional, a non-dimensional group. It's a semi-dimensional group. That's fine. 95% of the time, it's successful and clear and everyone knows what they're doing. And then someone shows up and says, I want to run a turbine on compressed CO2. Is that okay? And they go, oh yes, we can do that, that's fine. And then they forget that this number changes because it's not non-dimensional. If you change to CO2, CP changes a mile. And because CP changes, the capacity changes. So this curve moves. And if you don't take it into account, you're in trouble because your design won't work. And at Mather and Platt, when I was working in Manchester, they got in trouble for exactly this reason. They were selling pumps to pump oil, and the pumps had been developed and tested on water. And they did not make the correction for the difference in density between the oil and the water. Now, when you hear it, it's obvious, and they should have done it, but they got it wrong. And the consequence was that the pumps only generated 80% of the pressure rise they should. And of course, the customer said, that's no good. I wanted this level, you've given me that. And why, how did we get it wrong? Well, you ignored the density of the oil. So it really does matter. And I irritated people at Mather and Platt and at Rolls-Royce because I refused to use semi-dimensional groups. I used dimensionless groups properly all the time because I knew they were safe. They were correct. The semi-dimensional group works most of the time, but that means you've got to be really vigilant for when it doesn't work, and people aren't, so they make mistakes. The efficiency of the turbine looks like this. There's a curve at each rotational speed, and you will see that the peak efficiency is a function of the pressure ratio, and the faster the machine goes, omega over root T going up, the higher the efficiency. And this leads to the statement in Rolls-Royce that turbines like going fast. And we have a fundamental problem inside a gas turbine because a gas turbine is a compressor coupled to a turbine. Turbines like going fast, compressors like going slow, and they're coupled together. So always the turbine engineer celebrates when we learn that the shaft rotational speed in the engine has gone up, because we'll be getting better, and the compressors are getting worse. And the compressor engineers celebrate when the shaft slows down, because they're going to be higher efficiency and we're going to be worse. And that battle is an intrinsic in the gas turbine industry between two different camps of people. So yes, if you go faster, you get higher efficiency in a turbine, not in a compressor. This section mentions what I've already said to you about temperature. If it's a machine with heat transfer, you have to take into account the temperature ratio between the fluid and the outside world, which is represented by the wall temperature in this case. And if it's a cooled turbine, so you're squirting cold air in as well as hot air, then you need to take into account the temperature of the coolant, which is non-dimensionalized by the free stream temperature. I won't go into detail on that, but it comes in. There. I've finished. So that's the lecture done. I suggest what we do now is have a 10-minute break, and then I will go through the examples which are based on what I've just been teaching. Okay? You want a question before that?
Yeah, just remember you said the compressors and pumps, they're not good with low flow.
That's right.
But then you said the engineers are happy when you have low speed.
Well, when a machine starts, it's stationary. So you have to go through accelerating the machine. and whilst it's accelerating, the flow is low. And that's a problem because the machine is unstable. And you get it wrong, it will just vibrate and oscillate rather than actually accelerate, which is what you want it to do. Let everyone else go and do what they want to do for 10 minutes. You can continue the conversation if you like.
Why I get a signature here? This is all
I think for this one, yeah, it's not really necessary. For the subsequent one, I think we're going to go through.
Yeah, but the other is when state design. I think that's fine. That's up together.
Thanks for your email, by the way. I haven't had a chance to email you back. I thought about it all, but it was very helpful food for thought. So thanks very much.
Right.
I'll email you back to respond at some point.
Yeah, so you were wondering about compressors.
Then we're saying that you guys are happy with the spec, which is good, and then they're not happy with the why would they be happy with the slow if it's slow and they're not working good? That's what I thought.
When I talk about fast and slow, it's turbines. I'm talking about rotation.
It's not even really an important.
When I'm talking about low flow in the compressors and pumps, I'm talking about low Q, low flow rate through machines. The rotation speed may be high, but the flow rate is low, and low flow is the problem. Well, I think in practice your intuition that they ought to be related is correct, and that for good operation of the machine, you probably will scale volume flow rate and rotational speed. But in fact, they're independent. You can change the rotational speed by putting more fuel into your engine. It will change speed. You can change the volume flow rate by opening and closing a valve.
Yeah.
And so you might keep them in ratio, but you might take them apart. And if the compressor is rotating slowly and generating low pressure rise with low volume flow rate going through it, it's okay, that's all right. Where the problem comes in is when it's rotating fast with low flow, then it's in trouble. It will just go bang, 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 bang until you switch it on. Good.
Also, you know how I was talking about different issues.
Yes.
My dad has been saying this like 2 or 3 years. He keeps bugging me with this idea. He said, look, airplanes, when they want to go backwards, there's a car that comes in front of it and when I push it. Yeah, I mean, he's telling me I should research another way for the airplane to go backwards instead of having a contact with it. But I'm saying, like, it's not going to be discovered. Like, I'm sure people thought about that before. Why don't they have a mechanism for the plane to go backwards?
Well, the big thing with an aeroplane is you want it to be as light as possible. And so if you added onto it a mechanical drive, the driving wheels are making it backwards, it would add weight and cost to the aircraft, and you have to carry it for 10 hours at a time around the world. So that's why it's better to put a little tractor on the ground to push the aeroplane, because you don't have to take it with you. You can leave it on the ground. Or no, it would probably be 10 tons such a vehicle, and you don't want to carry 10 tons you don't need. So that's why you don't enable the plane to drive itself backwards. The plane does have thrust reversers, so it can make the engine turn backwards. Yes, that's already configured in there, and you can't use it when the plane is stationary on the ground. You can't use it in that environment because it creates massive levels of turbulence and scouring, and will move anything that's on the ground and move it around, blow it where in front of it. The e-flux, you use it when you land. It's called a thrust reverse. And for 5 seconds, 10 seconds, the flow is backwards. That is not backwards through the engine, but it comes out of the engine, turns around and goes backwards like this. And that makes the thrust backwards. And so the plane slows down rapidly. And the reason they do that, I was once asked the question, why Volvo? It's going to stop anyway. And the answer is it saves time, because they can get to the gate faster if they can stop. And that time is about 10 minutes. That time is long enough because it's worth having a thrust reverser for that reason. Because it's following the logic of carrying the kit you don't need. Carrying a thrust reverser, which is a sophisticated kit, is doubtful. But the airlines like that 10 minutes of extra time. And therefore,
So yeah, last time I wanted to fly to Switzerland, and the pilot said we had a delay, bringing the luggage into the airplane, and now we have lost our departing time, the slot, and we have to wait for another 80 minutes for the next one. I said, what?
yeah.
Well, it only takes like 1 minute to take off. I mean, it shouldn't take more.
Yeah, but the slot's gone in that
Yeah,
1 minute. Someone else has occupied
10
that
minutes
space.
is obviously, it's like 10 airplanes can you do that?
It's big economic deal for the airlines. They need to turn around and get back in the air. If you actually look at a jumbo and you ask yourself the question, where does it spend most of its time? And the answer is at 30,000 feet above 0.92. Literally about 90% of the time a jumbo is travelling 30,000 feet above 0.92. It's never on the ground. It nips down to pick up some people and back up again, and it spends its whole day up in the sky, and only every now and then nips down to get the people and go again. And that's the reality of a jumbo jet. It is a thing in the air almost all the time. Yeah. Continuously.
Otherwise, how can they, offer these cheap prices like easy jet?
It's phenomenal. I guess what the industry achieves. It's good fun doing it.
Well, about the other thing, we've got an appointment. Remember? Is it okay if we do it afterwards?
Yes, I think so. I know I saw your name on my diary this morning. So yeah, the only thing is I will need food.
Oh yeah, so you are.
After food.
So when was that date?
I haven't really defined it at the moment. This stuff is going to take about half an hour. I think. So if I assume that I'm through with food by 1 o'clock.
1 o'clock will be okay. And how long does that take? Because you have another appointment at 2 o'clock. So not in here, outside. So I need to leave like half an hour before we know that. So is it okay for half an hour? Would that be
Half an
enough?
hour is, Monty knows that when I get going, half an hour is not very long. But I might be able to get it done in half an hour. I'm going to be offering you a choice of project, and you might do it.
Well, obviously, yes. But what we are discussing now is not going to be more than half an hour. Because I don't want to...
Other stuff we got.
No, not now. After.
Well, what I'm doing is I can introduce the two ideas to you, and then maybe you make your decision subsequently.
Because I was thinking if it's not going to be enough, that's half an hour. After like 3 o'clock, if you're available, as you did mention, 1 o'clock.
TFN.
So we're that's my question.
Okay, so a bit of a trial use of document camera and shorter questions. I'm going to explain to you how to answer these questions. I would very much value your questions if you don't understand why I'm doing what I'm doing, because that's where we will really get through to the fruit. Yeah?
Are these on Study Direct?
Yes, the whole document is on Study Direct in typed form, because I did it a few days ago. Unfortunately, our printer's bust, so I had to write it out by hand so that I could show you it. My handwriting is not brilliant, but hopefully you'll be able to just about work out what I'm saying. The first question is, how does the volume flow rate through a pump at design point change when a similar pump runs 50% faster? Now, does anyone not understand the question? Right, good man. The idea is that we have a design of centrifugal pump, which is pre-existing, understood, available, and then you ask the question, how will the volume flow rate of a new pump that runs 50% faster, but is geometrically similar to the first one? Now, you might say, okay, you take the first pump and you speed it up. It's almost the same question, but I'm a bit pedantic about this because of the specific design of the flow angles inside the machine. So what I'm comparing here is not, in fact, a pump that's being run 50% faster. I'm comparing two pumps, each at their design point, one of which runs 50% faster than the other. And there's a subtle difference between those two sets of words. So the question is, what's going to happen? If the pump is 50% faster when you're designing it, how much more flow will that take, is my question. Now, can anyone suggest how we might go about answering that question?
Yeah, we need, make it dimensionless, first. Well, then take that, speed into account, for the first one.
Yes.
And then on the second one, we'll find it.
Yep. That's the right direction of thinking. We've shown you the flow coefficient many times this morning. Flow coefficient is the dimensionless number you need to answer this question. And when you've seen it, the answer is trivial. But when you've not understood it, it's weird. So we have to get you into the state of realizing, yeah, it's all right. Now, the dimensionless group that we've been looking at is the flow coefficient.
Is this being recorded?
Yes. This document camera and my voice. Yeah. So we take the flow coefficient, which is one of those things. I think that's probably a phi. And that's equal to Q over ND cubed, which is a dimensionless number. Now, the essence of this question is to assume that the flow coefficient for the existing design and the new design will be the same. All we know about the new design is it goes 50% faster. That means n, oh sorry, I've called it n because in another life we called it n. This is what in this lecture we've been calling omega. Apologies for that. So it's q over omega d cubed. Omega is the rotational speed. If the rotational speed increases by 50%, then is it not completely obvious that q increases by 50%? And that's the answer to the problem.
Is omega employed in industry as well? Or is it still n?
In Rolls-Royce it's not used. I think generally not. I think omega tends to be more scientific-y. N is more industrial. So q over omega d cubed is the same in the original design and the new design. The only change which has happened is the rotational speed has increased by 50%. To keep the flow coefficient at the same value, the volume flow rate must also increase by 50%. And so the answer is 50%. You know, and that is what the flow coefficient is expressing, is the relationship between the volume flow rate and the rotational speed.
You didn't specify the pumps are the same size, though, so D, you wouldn't know that D might not change.
Yes, I suppose what I ought to say, if the sole change is a change in rotational speed. Yes, so they're not just similar, they are actually the same size as well. Now, the next question addresses the point that you've just raised. So that's the answer to question 1. Question 2 says, how does the volume flow rate change at design point when a similar pump of twice the size is run? This time we assume the rotational speed stays the same. And all we do is we make the pump twice as big, keeping everything else constant. What will happen to the volume flow rate? Who can answer that question? Yeah.
Well, again, we use the same thing, but this time, you know, we write q over nd3 over q over n2.
Yeah, and what is 2 cubed?
Oh, that's 8.
And 8 is the answer. It's going to be 8 times the flow rate because the pump is twice as big. And it's d cubed in the non-dimensional group. So for the first answer, the answer was 50%. And for the second answer, because it's d being doubled, which is 2d, and 2d cubed is 8d cubed.
So does that mean the flow coefficient stays the same for the larger pump as well?
Absolutely, yes. Yeah. So we now have a factor of 8 in volume flow rate. And this is just showing that flow coefficient is a very powerful idea. It tells us how the volume flow rate will change when we change rotational speed and how it will change when we change the size of the pump. So that's the idea with those two. Question 3. What happens to the design point rotational speed of an aero engine turbine when the TGT, which is the turbine gas temperature, which is measured at the NGV exit inside the turbine, is increased from 1800 Kelvin to 1900 Kelvin? So this question is, again, comparing two different machines. One which is designed at 1800 Kelvin TGT, the other which is designed at 1900 Kelvin TGT. They're both the same diameter. They both have the same mass flow going through them, but the temperature's different. So how will the design change? Now, have you seen anything this morning that might allow you to answer that question? We've got a change of temperature, and we want to know how is it going to influence the rotational speed. How did we non-dimensionalize rotational speed in a compressible machine? Nope, you don't need Reynolds number. I'm making the happy assumption that Reynolds number is simply so high that it has no effect on anything. The way we non-dimensionalize rotational speed in compressible machinery is with a blade Mach number, which I've shown you, which is the blade speed u divided by the square root of, formally speaking, it would be gamma RT. The form I showed you was with gamma R replaced by CP, and then the semi-dimensional group, which is used in fact in industry, is N over root T. N is the rotational speed, that's what Rolls-Royce uses, and root T is the essence of blade speed without actually being exactly blade speed. Sorry, it's the essence of the speed of sound without being actually the speed of sound. So N upon root T is preserved. So if I take an existing turbine design and compare it with a turbine designed at a higher temperature, and the only difference is that the temperature has changed, what's going to happen to the rotational speed? It's going to go, yeah, it's obvious, well I hope it is. It's going to go faster. If you put hotter air into a turbine, it goes faster, always. And that's the way the turbine responds. The way you should look at this, like with the first two examples, we say the flow coefficient is going to be the same for the two cases quoted. In this case, we're now looking at a compressible machine. We're comparing design points on what is otherwise the same turbine. We make the assumption that the rotational speed, non-dimensional rotational speed, is going to be constant. And that tells us how the rotational speed must vary with the temperature. It directly follows. I sense you're not that happy with dimensional, with the rotational speed changing because the...
Omega sometimes says, and by here it says the U. The U there is...
U is blade speed, so U is equal to omega R, where R is the radius of the machine, and in Rolls-Royce, omega is called N. So apologies for my terminology, it's somewhat confusing. So N is rotational speed in RPM.
And R then?
Say again.
What do we do with the R then?
Yeah,
During
should
the transition?
R is constant, so it doesn't influence anything.
The radius, where did it go?
This one?
Between U to N.
Yeah, it's constant, it doesn't influence anything, so we ignore it.
Okay. Same for CP, because we always use N.
Yeah,
right?
yeah, that's right. I mean, if we could do this properly by using the speed of sound, or we can do it improperly as they do in industry, just taking the root of the temperature. It's the same thing, really. We get the same answer. And if you increase the temperature by a certain amount, then the N must go up. Otherwise, you're moving off design. The turbine is going to run at different conditions. The flow angles will be different. The Mach numbers will be different. The efficiency will change. Everything is odd. If we keep the design point, we know the performance is not going to change very much. Then we keep the N upon root T as a constant. That means higher temperature requires higher speed. They go together. And I can assure you that it physically happens as well. If you increase the temperature in a combustion chamber, the first thing that happens is the turbine speeds up. And that's simply because it does more work until it's sped up to the right temperature when it then stabilizes again. Can you see that dimension analysis is a bit wonderful? You know, it can let you answer stupid questions like, what's going to happen when it gets hotter? Bang. It's going to do this. And it does exactly that. In fact, it works out. I gave numbers. I ought to tell you how to calculate the numbers. We're going from 1800 to 1900 Kelvin. So you end up with the new rotational speed equals the old rotational speed times the square root of T new over T old. That's the equation I've actually solved, and the answer I think is 2.7% faster. So that's the answer to the question. We maintain the rotational speed coefficient. The increased temperature means the rotational speed must have increased. Right, question 4. How does the pressure in the combustion chamber change, starting at 40 bar, when we add fuel to cause a temperature rise, same as in the previous one, from 1800 to 1900 Kelvin?
So can you read that again?
Yeah, how does the pressure in the combustion chamber change, starting at 40 bar, when added fuel causes temperature to rise from 1800 to 1900 Kelvin? Now, this time I'm talking about a turbine. I'm not talking about a design exercise. It's a turbine inside an engine. The engine is running with the TGT, at 1800 Kelvin. And then pilot puts his foot on the throttle. No, he doesn't use his foot, does he? He uses his hand on the throttle, and he squirts in more fuel. More kerosene goes into the engine. Instantaneously, the engine cannot change rotational speed. It's just sitting there. It's got inertia, you know. It's a rotating mass of some hundreds of kilograms. It's not going to change speed instantaneously. But the pressure and temperature inside the combustion chamber immediately respond. Now, my question is, how much? What determines the pressure inside the combustion chamber when you increase the temperature of the combustion products from 1800 to 1900 Kelvin? What I'd be happy with is somebody working out what they need to do.
Can you just use E of V for MRT? You know that if the temperature is going to go up on one side, the pressure will have to change on the other, so using the ratios T1 and T2 with respect to E1 and E2.
Are you suggesting there that you keep the density constant? Is that the essence of what you're proposing?
I guess it would be why I was suggesting to use little v, so you didn't have an exact volume, so you were doing.
I don't think that's quite right. It's not far off. But this is a dimensional analysis lecture. Yeah.
I guess it's using the formula you have on 417, which is the mass times the square root of CP T1 over D squared.
Hooray. Good man. That's what's required. So question 4, the value m root T naught over P naught, I'm calling them naught here because they're stagnation quantities, but it doesn't make a lot of difference because the velocities in the combustion chamber are negligible. That group is a characteristic of the turbine. It's a dimensionless group. It will not change. The turbine will not operate outside that range until the pressure ratio is so negligible that it starts dropping. But provided we're in the sizable pressure ratio range on the machine, this is constant. I'm telling you that the temperature is going to increase from 1800 to 1900. The mass flow can change, but it takes time for the mass flow to change, because the mass flow is determined by what the compressor has been doing. So instantaneously, when you put in more fuel, the mass flow stays the same. In fact, it actually goes up a bit because of the fuel you've added, which has mass. But that is a 1% adjustment, so not worth worrying about at this stage. So the experiment we're talking about is you've got an engine running, it's at steady conditions, and suddenly you put in more fuel. The transient that occurs with constant value of this group, m root T upon P. That will not change. So we can calculate the change in the pressure just by knowing the change in the temperature. And the solution, I think I'd better fish it out on here so that I make sure I'm giving you the right number, because I don't have my calculator with me.
42.2.
42.2.
Yeah. The first one was 40.
Ah, yes, yes. Okay, so you've done the maths for me. Thank you. I'll call up the document so you can see it anyway, if it's going to appear. Examples, simple examples for dimensionless groups. I have to sign in again because the machine's got bored. This is the document you can download so as to give written answers to these questions. Oops, there it is. The capacity of the turbine is fixed, m root T upon P, so when the temperature increases, if we assume no initial change of mass flow, the pressure in the combustion chamber will increase to 41.1 bar. Yeah. So that's what will actually happen. This process is not just an interesting test of your thinking power, but something that's done on a daily basis in Rolls-Royce. The problem with a gas turbine engine, when you've built it, is it's very constrained in the way it can behave, because each turbine is of fixed capacity. The compressor cannot be run across its characteristic because the turbines define a line that it has to run on. So you can't really test out the behavior of a compressor inside a gas turbine because the turbines don't let it move. What this allows is that we can move it, because by putting in the extra fuel, making the temperature and pressure go up, the compressor suddenly has to generate more pressure rise, because that's ultimately where the pressure comes from, is from the compression system. And what this can do is to push the compressor up its characteristic towards surge. So you make it go to low flow, it becomes unstable. So what happens is, this is called fuel spiking, and in industry we test compressors by squirting in additional fuel to make the pressure rise, to make the compressor move up its characteristic towards stall and surge. And if you squirt in the fuel and the compressor then goes bang, 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 you know it's unstable. And this is how it's tested. So fuel spiking is part of the development of every engine. I was present in Alstom in Baden in Switzerland when they did fuel spiking on a huge gas turbine. They make a gas turbine that generates 250 megawatts. You know, it's a machine that makes you feel about this big when you see it. And they did fuel spiking on it. And for the same reason, they were testing the stability of their compressor. And it actually allowed us an opportunity to do a special experiment on the machine. So it was a very useful experience. Right, yeah?
Are we calculating that pressure spike in the same way as we did the temperature spike in the last one? So
No, it's not the same, because we're using a different dimensionless group.
As in the same style?
But it's exactly the same style. We equate the flow coefficient, the capacity before and after. So m root T naught upon P naught is constant. The total temperature changes, and that leads to a change in the total pressure. That's how we calculate. Yeah, sure, no problem. So we have, if we make these the old values, apologies for the double zeros, and these the new values, it's a matter of solving that equation when we know how total temperature is going to vary and the mass flows stay the same as the assumption. So we can delete mass flow from the equation, and you end up with the new total pressure is going to be the old total pressure times the square root of T new over T old. So it ends up with the same equation, but it's actually from a completely different non-dimensional group.
Do we need to memorize these non-dimensional groups?
These, yes. In general, no, but these are, from my point of view, completely prosaic. They are part of describing turbomachinery. So the n root T upon P, the n upon root T are bread and butter.
I think you're talking about exams.
Yeah, no, I would expect you to know these groups. They are, the only tricky bit about them is they're semi-dimensional. they're not actually dimensionless groups. And if you chose to use the dimensionless groups, which would be, as I wrote here, U upon root gamma RT, and this one would have CP T naught over AP naught, they're dimensionless, which means you can verify them when you're remembering them to make sure you've got all the terms in there. The semi-dimensionals are fine until someone nasty springs a question on you with a different gas or a different liquid, and then you've got to know the full dimensionless group. So, as I say, my personal approach was to use the full dimensionless groups, because then you don't get it wrong. Right, what am I doing? I'm still recording and the document camera is on. We now come to question 5, which is my sales engineer question. I've already talked to you about what the sales engineer has to do. The guy is phoned up by a customer, and the customer says, I want a pump. I want a pump that will shift 15,000 litres of water per hour. That pump has to push water up 15 metres. And it's got to run at 3,000 RPM because I've got a spare squirrel cage induction motor to drive it, which has a synchronous speed of 3,000 RPM. And the question that the sales engineer has to answer, first of all, is what type of pump should I offer to this customer? Now, who can remember from an hour ago when I told you how to do this?
You need to find a specific
Speed.
Yes.
Specific speed, yeah.
Which I can't remember.
No, well, no, it's a horrible group, isn't it? This one I would not expect you to remember. I think it's too nasty.
Something.
The rationale I would like you to remember, but not the equation. So, i.e., if it were in an exam, I would quote the specific speed. Let me just change back to the PC. There it is. I cut and pasted it out of the presentation because I don't remember it either. So that is the group which I showed you in the presentation. We have 15,000 litres per hour, which you need to... You need all the variables to be in SI in order to get the right value of specific speed. In industry, they do horrible things. You know, the specific speed is in gallons per hour, or gallons per fortnight second or something. It's just, you know, horrible units, cubic feet and RPMs and all sorts of stuff. But the idea is the same, but they never get non-dimensional. They're not bothered about it. And they still call it specific speed. This is real specific speed, non-dimensional specific speed. Yep.
Is the head height 150 on there, and it's 15 on the question?
Right, that's because when I first wrote this, I used 150, found that the specific speed was a bit low, so reduced it to 15, and so a typo, apologies, that should read 15. I think I changed this part of the answer to give that, but I missed the fact that there I'd written 150. So 15,000 litres per hour is 4.17 times 10 to the minus 3 cubic metres per second. I never find cubic metres per second particularly helpful variable, but it is a ton of water per second, a cubic metre per second. So it's a thousandth of a ton per second we're talking about. The rotational speed is 3,000 RPM, which you need to convert into radians per second, which hopefully you all know how to do. So 314.16 radians per second. Radians per second is always approximately 1 order of magnitude smaller than RPM. So if you're wanting to check when you've evaluated a radians per second, check that it's about 1/10 of the RPM. If it is, you're okay. If you've done it otherwise, then you need to change it. The head rise should be 15 metres. Apologies for the 150. You calculate the pressure associated with that head rise, as simply rho gh. So density times the acceleration due to gravity times the height. And that gives you a pressure rise of 1.47 times 10 to the 5 pascals, which is 1.47 atmospheres pressure rise. And if you plug those three into this nasty expression and you get your pressing buttons right in your computer, you'll come up with a specific speed of 0.48. And if you look at the graph which I showed you in the lecture, you will see that 0.48 is a kind of low number. I think I gave a typical number for centrifugals as 0.4. So we're certainly talking about a centrifugal type pump. So that's the first thing the sales engineer has understood, is what the customer's asking for is a centrifugal pump. It's not an axial or a mixed flow, it's a centrifugal. So he picks up the brochure which is for centrifugal pumps, and it has a list in it of 50 different centrifugal pumps, and he will find one which is sized correctly for the flow rate that the customer wants. Because knowing that it's a centrifugal pump doesn't tell you what its pressure rise is or what its flow rate is, but what its characteristics look like. Having got the characteristics, you've then got to calculate how big is it. Once he knows how big it is, he can be specific about which one to offer to the customer. And question 6 takes that forwards. Question 6 says, for the pump in question 5, what is the diameter of the impeller if the flow coefficient is 0.5? How do you use that?
Q over ND.
Q over ND cubed. Cubed, yeah. Yes, you do. So the flow coefficient is Q over ND cubed, and that has got to be 0.5. We've got
Q.
Yep.
RPM, which is like there.
So that is Q. Yeah, we know Q. We know N. Therefore, you can calculate D from that number, and the answer was 29.8 centimeters, I think.
Just so,
Yeah, 29.8 centimeters.
so we just don't be, could you just scribble on that zero that you put? Because I don't know if I went home and read that, I'd be confused.
What you want me to do?
You said it's equal to zero eventually.
No, sorry, I was halfway through.
No, that's I'm gonna go home and
I was halfway through writing Q over ND cubed again and realised it was a waste of time. So yeah, it's not a zero; it's just a silly. But we know Q, we know the rotational speed N. The question tells us that the flow coefficient is 0.5. That is taken from the company charts. You know, he knows the specific speed, he knows the type of pump. So the question would be, well, what sort of flow coefficient do these pumps have? And the answer would be, well, about 0.5. And therefore he can use the flow coefficient to evaluate the D, and we get an answer which is 29.8 centimetres. So that was big.
Is that, that shouldn't be in millimetres, so it's in SI, so do you then just change that into centimetres?
I've changed the units, yeah, just to make it convenient. Not to confuse you, but to make it convenient.
How close is like kind of generally acceptable value? Because you talked about when you're in a company, you're going to have a range of pumps to choose from.
Yes.
And you're obviously going to have to pick the best fit.
Yeah.
But there's going to obviously you're never going to hit bang on. You talked about earlier getting 80% of the right value. That's obviously not acceptable.
Yes.
What kind of range is?
You're absolutely right in that there is a tolerance, and it depends on your relationship with the individual that's asking. And if the person requires the pump to be exactly as he's saying, you need to design him a new one, because it's very unlikely that the pumps you've got are precisely right for the conditions he's after. When I was working at Mather and Platt, we had an instance where a customer asked for a duty which really none of the pumps did. And the sales engineer still sold him some pumps. And what was going on was the pumps didn't really generate enough head according to what the customer had asked for. But the sales engineer was of the opinion that the customer didn't really need that head anyway. So what happened was the pumps were made and they were put in pump test at Mather and Platt in Manchester in a line across the floor, each pump being connected to the next pump with a pressure gauge. So you have 6 pumps in a line with pipes between them and 7 pressure gauges before and after each pump. And the customer sent a guy to come and check that the test was accurate, that the pumps really were doing what they were supposed to do. And what Mather and Platt was doing was cheating. And what they'd done was, because the pumps actually didn't generate the head that was specified in the contract, they'd changed the setting on each of the gauges to show higher pressures than they were actually measuring. So we had a line of gauges. Now, the surveyor who had come to test that everything was all right came with his clipboard and his pen, and he carefully read all the gauges, and they were all showing the pressure rise that should be happening. So big tick, everything's all right. And then someone switched the power off. And all the pumps stopped, and the gauges were still reading dum, 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 dum. And the thing that I always remember is this inspector looked at it, smiled, and walked away. He didn't do anything, because he knew the customer had overspecified the required pressure as well. But this is the kind of thing that goes on in industry, and you've got to keep your eyes open, because you're dealing with human beings. Right. I think that's reasonably it for the day, but there is a question, isn't there, which is outstanding, which I think I don't intend to work through with you at this time. Example lecture 2, this one here. Are you seeing this? Yeah. So if we open that up, this is I think, if I remember rightly, a rather more complex dimensional analysis problem. A test water pump at a speed of 2,000 RPM shows that the flow rate is 0.085 cubic meters per second with 32 meters generated head. This point is the maximum efficiency point, and the shaft power is 35 kilowatts. A new pump is to be made with all linear dimensions increased by 20%, and the new pump is required to pump water at a volume flow rate of 0.16 cubic meters per second when operating at maximum efficiency. Maximum efficiency and design point are synonymous. So if I say maximum efficiency, I mean design point, and vice versa. And the problem that you're asked to do is find the required rotational speed, the generated head, and the shaft power, and the efficiency for the new design. This hopefully is a matter of pulling together the ideas I've been showing you and applying them in one case. What I would propose to do is next lecture to go through the solution of this with you. For those of you who like to have the solution available, it is in next week's lecture. It's there, you can read it if you choose. But understanding this and how it works will help you go forwards. Right, any final questions for today? Okay, well, thank you very much. See you next week.